Okay, now it's recorded. Thank you very much, Bernardo. I always keep forgetting. It's a catastrophe. So, Gerhard, please go on now.
Sorry.
Gerhard, please go on now. Yeah.
These pictures hide part of what I wrote. Could you remove these, please?
Which pictures?
The pictures of part of the participants. I'm very pleased to see them personally, but at the moment I would prefer if what I had as, so to say, an inscription on the blackboard in full.
I think
could you please? Now I see you.
Yeah. On the top of the pictures of the participants, there are some symbols. For instance,
where I could cancel them. Yes. Okay. Fine. Please.
And no, that's not it. Then there are two blue bars on the top of the page where you see the participants.
I do not see it at the moment. I have only a good view of your study. Well,
so again, on the
please return to the former picture, and I hope to be able to cancel these personal pictures.
I'll go back to this.
Well.
And on the top, on the right top, you see a button for Ansicht, the right upper corner.
Yeah, Ansicht, and I should cancel this.
Yeah, if you click on Ansicht.
Galerieansicht.
Yeah, you have Galerieansicht or Sprecheransicht.
Well, I have many more people.
Yeah, please go to Sprecheransicht.
Click to Sprecheransicht. Where is that?
So first click on Ansicht.
This is Ansicht, yes,
and then click on Sprecheransicht.
This must be below.
Yeah.
That's nowhere. I have aufnehmen, Chat, Teilnehmer. Should I?
No, not in the.
Oh, that's not good.
It's on the right upper corner.
In the right upper corner.
Click on Ansicht.
Ansicht, yeah.
And then you have the choice
Sprecheransicht, yeah, okay.
And click on Sprecheransicht.
Yes, I did. And now we need
Now we need a. Is it okay now?
Yeah, fine. Okay. Oh, no, not yet. Well, that's all right. Now, please, page 10.
Yeah. Page 10 is here.
Page 10.
Page 10 is here already, Gerhard.
Not here. I still have you in front.
Mr. Ting, can you see page 10? In handwriting?
Yeah, I can see page 10.
Now I have Mr. Ting in front. And on a small picture, I have, well, the beginning of the notes for today. Near-rings.II.2, session on the 15th March, but in a very small section.
That's strange, but can you do it from your notes?
Yes, but the
Because
participants wouldn't see anything.
Because the other participants obviously see this page in Mr. Ting, you also see it in a
Gunther,
large form.
I think that it's just you need to go to the upper right, and there is a bottom that like something like view or something like that, and you should select standard. Not Gunther, Professor Betsch.
Ah,
Because in that way you see the Professor Gunther screen and not us.
so Gerhard, please go to which button did you say, Bernardo?
In my computer it's
Page
called
10.
Vista, so it should be something like view, or I don't know, yours in German,
Yeah,
I guess. So
so there should be something, Gerhard, on your screen, view or Ansicht.
The participants should see page 10.
They do see it, but you don't see it. So
is
the
in the
participants
right
see
up
page
corner.
in the right upper corner, you should have something like view or Ansicht. I go back to the screen now. Okay, do the same as before. On the right upper corner, go click Ansicht. As before.
There is no Ansicht.
Yeah, but Gunther, you need to
only
be
chat and
Gunther, you need to be presenting, otherwise the option for selecting how to view while someone else is presenting the screen is not available.
Oh,
here is Ansicht. Okay, very good.
and you
should I now click Vollbildmodus or
Yes,
Galerieansicht?
Yes, try Vollbildmodus.
Vollbildmodus, very good. Yes. ESC is my escape. Where is it? Ooh.
So Gerhard,
here we go.
yeah.
Thank you very much.
Thank you, Bernardo.
Welcome.
Yeah, this I just put together the concepts we had so far. I repeated the concept of nearing. Oh, could you lift it up? I cannot move it. I cannot. Yeah.
Okay.
The concept of a nearing, and my point is that I have a different distributive law from last semester, and then we discussed the correspondence of sharply two transitive groups with near fields, and I mentioned that, or I put forward the concept of planar nearings or planar nearing, and of a Ferrero pair. And if we go Ferrero pair that consists of an additive group, which will be the additive group of the nearing to be constructed, and a non-trivial group of fixed point free automorphisms of n plus, of course, and the additional condition that -5 plus the identity on n is a surjective. This should be with a C. That's, sorry, that's German. This is automatically fulfilled in the finite case. And we are now in a position. Let us assume we are given a Ferrero pair, automorphism group and additive group. Then we can build a balanced incomplete block design. The script B is the set of the blocks, N is the set of the points. And the incidence relation is element relation. And we start from the orbits of V on the non-zero elements of N. And then we, and then we apply translations, and this gives us the blocks. We could also, and this was historically the first attempt, from a planar nearing, you can form a balanced incomplete block design. And then further investigation showed the real kernel of what is going on is the Ferrero pair. And from the Ferrero pair, we can, from the Ferrero pair alone, we can, well, with a little use of addition in N, we can form a balanced incomplete block design. And how we get from a planar nearing to the balanced incomplete block design, that's pretty clear once we made the construction from Ferrero pair to planar nearing. So the first thing we are now going to do is to construct from a Ferrero pair and a planar nearing. And then we try to make sure that this is, the reverse is also possible. From a planar nearing, we can derive a Ferrero pair, which yields this planar nearing. And of course, it is, one wants, given an additive group, one wants a non-trivial, interesting group of fixed point free automorphisms, and so to say a good breeding stock of 6.3 automorphisms are the Frobenius groups, which are quite frequent, and I decided that it might be advisable to discuss the few definitions of Frobenius group, which it's not clear from the very beginning that they are equivalent, and a few very few properties of Frobenius groups. One concept is a Frobenius group is subdirect, semi-direct product of a group of automorphisms, which with a group on which it acts. So I think we deal first in this triangle, and this will be possibly in the next session. I will say a few words on Frobenius groups, and then we go on. Yeah, we now upper part of page 11, please. Fine. If we assume we are given a Frobenius, no, we are given a Ferrero pair, then we have a partition of n into 0 and blocks of orbits of equal length, which will be our basic blocks, as Jay called them. We start with these blocks, and we take representatives of these orbits, call them EI. They are all of equal length because phi is 6.3. So from a representative of this orbit, a certain other element B can be reached only in one way. And the union and those elements which which will, by multiplication from the left, lead to 0. They will be A. A is a union, but this is also a union of orbits. And A times x for all x in N will be 0 if A is from capital A. Now, we assume a given Ferrero pair, and we define a multiplication on n plus in such a way that if phi A is this element in capital Phi, which maps the representative to A, then A x multiplication of x from the left by A will be phi A of A. If A is in capital A, then AX will be 0. And we will show that this yields a planar Near-ring n plus point. First, we show distributivity. This is almost trivial. As part of R, we show distributivity. If A is in capital A times x plus y is 0, and AX is 0, and AY is 0, so AX plus AY is also 0 if you multiply by A individually, or if you multiply the sum. Now, if A is not in capital A, if we call this n star, Then we apply the automorphism property of VA and get again this distributive law. The next point is a bit, could you move up just a bit? Fine. To show the associativity of this multiplication. To show A times BC is AB times C, we have to distinguish three cases. First, if A is in capital A, then A times BC is 0, and AB, C is 0 times C, and this is also 0 since we already proved, this was done by Günter Pilz last semester, that this is zero symmetric. And in this case, we should argue that we defined left multiplication by 0 as 0. Then the second case beta is A is not in A, but B is in A. Then we have AB is VAB. This is in the orbit of B, but this must be contained in A. So AB must be AB times C must be 0 times C. This is again 0, what we have already. On the other hand, if A times BC, BC is 0, so A times 0 is 0. So the real interesting case, could you please a bit move up? Fine. The really interesting case is A is not in small a is not in capital A, and small b is not in capital A. Then AB times C is VA times B times C. Phi B is not in A, it remains in the orbit of B. So it's phi of phi B equals C. And A times BC is VA times VB of C. BC is VBC, and left multiplication by A means we have VA combined with VB is C. We want these two things to be equal, so we have to show that phi sub VAB is the combination of VA and VB. Well, that if B is in the orbit of E phi of E in the orbit of EI, then VAB is also in this orbit. But this is also VAB is VA combined with VB EI. And on the other hand, we have this, if we, this means we, what this phi sub VAB of EI is VAB of EI, and this is the same as it's now hidden. So in any case, we get the same, and we have the conclusion that n plus times is a near-ring. Now for planarity, we have to show that if A is not equivalent to B. That means it is not the case that for all x, ax is equal to bx. We have the planarity condition. That's my abbreviation is PL. And this must have a unique solution. Again, the proof is divided. We first consider the case that A or B are in capital A, so AX or BX is always 0. Assume B is equivalent to 0. Then the planarity condition reduces to AX is C. But A is not equivalent to 0. So AX, which is Vx AX, phi A must be an automorphism, so a bijection on the orbit of C. So there must be exactly one x in the orbit of C, such that this planarity condition holds. Could you move up a bit? Well, yeah. Actually, in this, if A is equivalent to 0 and B not, then we have Bx is equal to minus C. B is not equivalent to 0. This is the same situation as before. So in both cases, the planarity condition holds. Now, we have to consider the case that A and B are both individually not equivalent to 0, and they are not equivalent to each other. Otherwise, the planarity condition doesn't apply. The planarity condition becomes minus Bx plus Ax is equal to C. And we can write this as minus phi B plus phi A. Addition of an automorphism is not defined. We could the combination. This is given by the group group multiplication. But nevertheless, if B and A are not equivalent, this is not equal to the 0 map. It must be an injective mapping. And I multiplied this now with phi A to the minus 1, then this becomes minus phi B times combined with phi A to the minus 1 plus 1. And this is then phi AX equals C. This is no longer an automorphism, but it's still injective. And by the special condition, which is supposed, together with the definition of a Ferrero pair, this must be surjective. In the finite case, a surjection between a surjection of a finite map of a finite set onto itself, which is injective, is automatically surjective. But in the infinite case, this can be different. In any case, we have this condition. It must be injective. This is injective, and by this special condition, it is also surjective, hence bijective. Hence, we have exactly a y such that this of y is C, and well, then we can find an exactly one x, so that phi AX is y, and this proves the planarity condition. Okay, it's a bit, maybe a bit involved. I would, if you, I think you have access to these notes, so I would advise to recall these steps.
May I interrupt you? I think I found a typo in the definition. May I go back to page 11?
Right, please do so.
So this is page 11, and here you have the definition.
On page 10, you could find also on page 10. Go back to page 10, please. I repeated this to have it together. That's Ferrero pair.
Yeah, no, it's not here. No, I mean something different. Here on page 11, you define the multiplication in the middle of the page in the form a times x is defined by phi a of a, but it should mean phi a of x.
Oh, I'm sorry. Yeah, that's a mistake. I apologize.
Yeah. So just for the other people in the audience, please correct this.
I missed that.
Yeah,
could we go?
Can happen all the time.
2.2.
Okay, here we are.
Now there are well, what do we have? We were able from a Ferrero pair to construct a planar near-ring. If we want to make sure that all planar near-rings may be obtained in this way, we need informations or observations on planar near-rings and certain definitions and notations, such that we will be able from a planar near-ring to reconstruct, to dig out Ferrero pair from which we could have derived this planar near-ring. Okay, let N be a planar near-ring. And that is not new, we define A and we define N star. Normally N star in a field, this is normally the multiplicative group. In this case, we have to exclude the elements which by left multiplication turn everything to 0. Okay. It's, I think, relative, bit down. If we have A and N star, then A and B are certainly not equivalent. So we have AX plus 0 times X plus C, which is equal to C, must have a unique solution. So we have that such an equation with X on the right is always soluble in a unique way. That's very important, and we shall use that frequently. The unique solution of AX equals A is denoted by 1A. This plays the role of identity in the case of the element A, and we will see that this is not restricted to the element A. A first remark, it is possible that A sub A, 1A is the same as 1B, despite A is not equal to B. For an element in N star, we define BA as all those B for which one sub A has this unity role. For these elements, one sub A is a right identity. For all elements in B sub A, it will turn out these are the basic blocks. They will turn out to be more or less the orbits under the group we will construct. L will be the set of all those YL. This will be clear later. One sub A for all A and N for all distinct, of course. If it's a set, we have to have elements just once. One sub A for all A in N star. Now we have a few properties of equal weight. I think 3 could be well named C, but now let it be. It is clear that since A is always in BA, and for all and A union N star is N, we have this one that's absolutely trivial. And if we multiply an element B in BA from the left by an element of N star, we get an element in BA, and we get all the elements. So this is certainly not empty. For instance, A belongs to it. And the third and much more important thing is for A in N star, the B sub A under usual multiplication in N is a group. We will show it's closed under multiplication. It's a semi-group. Second, it has a right identity, and it has a unique right inverse, which is sufficient to prove that it is a group. First, if X is in N star B, yeah, well, this must be contained in BA. When we have XB, 1 sub A is X, B1 sub A is equal to XB. Hence, XB must be in BA. But yeah, if X is in this way in BA, then XB is in BA. So it's, yeah, and BA has a right identity. This, if you restrict N star to BA, then you have the multiplicative closure. BA has a right identity, and assume that A prime is the unique solution of AX equals 1A. This is a candidate for the identity of the group to be detected. Well, then we have 1 prime. A sub A is 1 prime. That's a and this implies implies that A prime is BA, and if B is right inverse of B in BA, there must be such an inverse because of the planarity condition. No, sorry. We have, if AX is 1A, then A prime is in BA. And now we assume that B is in BA with an inverse in BB. Could this B be in the intersection? Although, or in the intersection, and B sub A not equal to B sub B. Assume we have an element in this intersection, then C1 sub A must be C equal to C1 sub B. But this, because of the uniqueness given by the planarity condition, means that 1 sub A is 1 sub B, and these two BA and BB coincide. Hence, we know this is a group. The inverse lies, the inverse of an element A is situated in BA itself. And we have also that BA, if BA intersection BB is not empty, then they must coincide. Well, now we have a group, and it is, of course, it needs not being a prophet. This is a good candidate for the group which we need to form a Ferrero pair. We have a mapping from BA to BC, X in BA mapped to X1C in BC. I prove that this is a group isomorphism. First, it's a homomorphism. That's relatively easy. Good. Vxy, this is xy times 1c. This is xy1c, and well, we can insert this one sub c, and so we have this simple condition of homomorphism. Phi is in homomorphism. Then, could you move a bit up? We get again by this uniqueness condition that 1 sub A is 1 times 1 sub C is 1 sub C. And if X and Y are under this mapping, which we consider equal, then over a few trivial calculations, we get X equals to Y, and this means that Phi is a monomorphism. Finally, we show that it is an epimorphism. If Y is in BC, then Y, assume Y is in B sub C, then Y I sub A is in BA, and then we make these, Y1 sub A is 1 sub A times 1 sub C. And because of what we have above, Y, this is 1 sub A, sub 1 sub C, and this is 1 sub C, and this is Y, so it's an epimorphism, and this means it's an isomorphism. Furthermore, yeah, this is now a new thing. We show that 1 sub a is a left identity of n. We consider the equation star 1 sub a times x is 1 sub a times d for a d in n, arbitrary d in n. Then this equation star must have a solution d. No, I should say, then this has a unique solution, and the d is a solution, and 1 sub a times d is a solution. So we have equality. So we have 1 sub a d is equal to d, and 1 sub a is a left identity of n. Could you move up a bit, please? Next page, please. Günther, could you move up a bit?
Yeah. No,
This must be
so 1 moment.
page 16.
Mhm.
Page 16, please.
Yeah, 1 moment.
2.3 main result.
Yeah. Okay.
Very well, very well. The main result in this context is not only how we get from a Ferrero pair a planar nearing, but the point is each planar nearing n plus times can be constructed from a Ferrero pair phi n according to 2, 1. Remember, we made this construction, and in 2, 2 we listed a few properties of planar nearing. In Glee's book, this has the enormous, all these observations are listed under fundamental theorem on the structure of fundamental theorem. It's a bit, for my relatively modest side on the world, this is a bit too, it's too much. It's not a fundamental theorem. A fundamental theorem is something else. We assume the situation, we are given a planar nearing, and using the observations which we made and the notations which we introduced, we will find, or we try to find, we will find a Ferrero pair. BA is has the meaning which we introduced. B. It's yeah, the elements B with B times 1 sub A is yeah B. And for B in A we have phi sub Bx is Bx. And now we consider all the phi sub B in BA. And our intention is to show first phi is a group. Yeah, well, we know BA is a group. Phi is a subgroup of the automorphisms of the group N plus. And this group acts is a group of regular automorphisms or fixed point free automorphisms. And B minus phi plus 1 sub n is surjective for each phi in the complement of 1 in capital Phi. Okay, this is now what we have to show. Proof A, I show that's homomorphism. Well, that's clear. Phi phi bx. Yeah, well, this is simply the definition. So this phi b must be a homomorphism. Capital Phi is supposed to be a group, and no, we prove that it is a group, and this is a picture under this mapping Phi. So this is homomorphism condition. Bx equals 0 has a unique solution x equals 0. Hence, this must be a monomorphism. And if A is in N, Bx equals A has a unique solution. Hence, A be an arbitrary element in N. Bx has unique solution. Hence, Vb must have epimorphism. We have Vb is an automorphism. And it's clear, again, from what we derived from the planarity condition, it must be regular as a permutation on BA. Then we need this condition N, the number of equivalence classes on N with respect to this equivalence must be at least 3, which means if this is so, no, yeah, if this is so, then phi must have at least 2 elements, and this means that phi is not the trivial automorphism group. Now we take an element phi sub b not equal to 1 in capital Phi, and we consider 1 sub ax is bx. This must plus c, that's planarity condition, which must have a unique solution for each c, and bx is phi b x. Now we come up with minus phi b plus 1 sub n times x is c, and this is true for this has a solution x for any c, so minus phi sub b plus 1n must be surjective. Conclusion: this phi n is a Ferrero pair, and well, basically we just converted what we did before. It's a Ferrero pair, which yields our near-ring N. If we had now, what about if we had started? If we had started with BC unequal to BA. Well, we go back to the to 2, and we know that BC to BA, B to BB is B1 sub C is a group isomorphism. This means that it is a group isomorphism, and we know that 1 sub C is a left identity. So if we take an arbitrary B1 sub C in BC, then B1 sub C times X is B1 sub C times X equals Bx for each X in N. So B in BA and B1 sub C. B is in BA and B1 sub C. BA define the same automorphism. They define the same automorphism, and we get the same group, capital B, from each of the BAs of N. And furthermore, for A, for A, 1 sub A in N, phi of 1 sub A is exactly our BA from which we started. So what I announced proves to be true. These are exactly the orbits of the group which we detected, and the group which we detected was actually one B sub A. And this means that N star must be a union of orbits. And of course, if you take away from N a union of orbits, then the rest must be the union of orbits as well. And this means N plus point is one of the planar near-rings which we can construct from the Ferrero pair phi N. All right. Now let me give a short preview. In the next session, we shall study circularity. Lie was, there is no more page to be shown. Lie was very, always wanted to find combinations between near-rings and geometry. When he first came to a near-ring conference in Oberwolfach, he presented the findings of Angel and himself on geometric interpretations of near-rings. And the circularity is one of the most interesting interpretations, and the motivating example is the multiplication of complex numbers. If you remember, if you multiply two non-zero complex numbers, you have to add the argument and have to multiply the the absolute values. Now, if you consider, I shall write this down on a page which you see in a week. If you multiply a complex number with a from the left with a complex number of absolute value 1, it means a simple rotation. So you get by modified multiplication of complex numbers, you get a very different and I think quite interesting description of circles. And well, this will be then, we will discuss this and we'll see, and we will also, I think in the next session, we will discuss a few properties of Frobenius groups. So I think that's enough for today, and we see you in a week. See you again in a week.
Okay.
Okay, thank you very much.
See you.
Thank you. Nice.
Yeah, so thank you very much, Gerhard. And I think we can close this session and look forward to next week.
Okay.
See you.
Good, see you. Oh, Bernardo, just
Yes.
one question. Did you get the certification for your?
Okay, it was not there on Friday evening,
Mm-hmm.
but today I haven't checked.
Because it should be finished by now, yeah.
Okay, I'll check now and I'll write you an email. Anyway, Friday evening was not there.
Okay, thank you.
You're welcome. Bye.
So bye-bye.
Bye.
Yeah, good.
Bye-bye.